Hey everyone, I'm so excited to jump into today's deep dive. We're tackling a paper you sent in, Raise a Child in Large Language Model Towards Effective and Generalizable Fine-Tuning. The title alone, right? It's about fine-tuning these massive language models, the ones with billions of parameters. But here's the catch. They're doing it with limited data. And the approach is fascinating. It's like, raising a child. Have you ever heard of child networks?
The paper addresses a classic challenge in machine learning: overfitting. Imagine teaching a child the alphabet using only a handful of words. They might memorize those specific words perfectly, but struggle to recognize letters in new contexts. It's the same with large language models. If they're trained on a tiny data set, they risk memorizing the quirks of that data instead of learning the underlying patterns of language. This leads to poor performance in real-world situations.
Right, so they're over-specialized, not very adaptable. So how do child networks come into play? The paper talks about this technique called child tuning. What's the gist of it?
Child tuning focuses the training process on the essential parts of the model. Instead of updating all the model's parameters during fine-tuning, child tuning selects a subset of those parameters. This forms a child network, and these are the parameters that get adjusted during training.
Interesting. So it's a more focused approach, but then the paper goes on to describe two different types of child tuning, task-free and task-driven. Child tuning and child tuning in. What's the difference between the two?
It boils down to how that child network is chosen. In child tuning, the parameters are picked randomly, and they add some noise during the training process. This randomness prevents the model from getting too fixated on that limited training data, encouraging it to learn more robust and generalizable features.
So it's like introducing a bit of chaos, controlled chaos, of course, to make the model more adaptable. What about the task-driven approach? Child tuning sounds a bit more strategic.
It is. Instead of random selection, child tuning utilizes Fisher information. It helps pinpoint the most relevant parameters for the specific task. Think of Fisher information as a way to measure how sensitive each parameter is to changes in the task's output. It tells us which parameters are the key players for a given task.
Got it. So it's like creating a tailored curriculum, focusing only on the skills needed to excel in that specific area. But does this actually lead to better performance? I mean, how do we know this child approach is actually working?
They put child tuning to the test using the GLU benchmark. It's a collection of different language understanding tasks used to assess how well a model can generalize its learning. And the results: both child tuning and child tuning outperformed standard fine-tuning methods across the board.
Wow, that's impressive. So it's not just a cute analogy, it actually translates into real improvements. Did the paper mention which of the two approaches performed better?
Generally, child tuning, the task-driven approach, produced better results. It seems that being selective about which parameters to train, rather than choosing them randomly, can really enhance performance, especially when you're working with limited data.
That makes a lot of sense. So we're seeing tangible benefits in performance, but what about the bigger picture? Does child tuning do anything beyond improving performance on a single task?
This is where things get really interesting. The paper goes a step further. They explored how well these child-tuned models can generalize to new, unseen data. They ran generalization experiments, testing the models on data from different domains and even entirely new tasks.
Right, because that's the ultimate test. Can the model apply what it's learned to situations it's never encountered before?
Exactly. And what they discovered was that child tuning, particularly the task-driven version, significantly boosted the model's capacity to generalize. This suggests that focusing on those most relevant parameters doesn't just improve performance on a specific task, it helps the model develop a more robust and flexible understanding of language in general.
That's fascinating. It's like we're moving away from just teaching the model what to think and towards teaching it how to learn. But wait, the paper doesn't stop there, right? They compared child tuning to a whole bunch of other fine-tuning methods. Can you break this down for me and our listeners? What other methods are we talking about? And how does child tuning stack up against them?
They examined a variety of popular techniques, things like weight decay, top tuning, mix-out, Rick-Adam, and R3F. Some of these methods showed slight improvements over standard fine-tuning, but child tuning consistently outperformed them, demonstrating significant gains in both performance and generalization, and across a range of benchmarks and data sets.
Wow. So it sounds like child tuning is a real game changer. But I'm curious, you mentioned that they compared child tuning with other methods. Did they ever try combining child tuning with any of these other techniques to see if they could get even better results?
That's a great question, and you're right on the mark. The paper does suggest that combining child tuning with other techniques could potentially lead to even further improvements. It's like giving the model an extra set of tools to enhance its learning. But this would require more research and experimentation.
Now that's intriguing. I wonder if there's an optimal combination of techniques out there that could unlock even greater potential in these massive language models. This whole fine-tuning process is like a balancing act, isn't it?
Absolutely. We're aiming for that sweet spot, where the model excels at a specific task, but also remains adaptable to new situations. And that leads us to another area where child tuning truly shines: low resource scenarios.
Low resource scenarios. Can you remind me what that means again?
These are situations where you have very limited data for training the model, maybe just a few thousand examples. It's a common challenge in real-world applications, especially in specialized fields where labeled data is scarce.
Right, so standard fine-tuning in those cases would likely lead to overfitting. The model would just memorize those few examples and wouldn't generalize at all.
Exactly. But here's the remarkable thing. Even with such limited data, child tuning, particularly the task-driven approach, can still help the model learn effectively and avoid that overfitting trap. Remember how it focuses on the most relevant parameters? This makes the model less prone to distractions from noise in the data and more likely to learn the true underlying patterns, even from a small sample.
So by zeroing in on those essential parameters, child tuning helps squeeze the most out of that limited data. It's like teaching a child with just a few carefully chosen books, instead of overwhelming them with an entire library. When I first saw the title of this paper, Raise a Child in Large Language Model, I'll be honest, I thought it was a bit gimmicky. But the more we dive into this, the more I realize how powerful that analogy really is.
I completely agree. It's more than just a clever title. It reflects a fundamental shift in how we approach training these massive models. It's a move away from brute force training and towards a more nuanced, selective approach that prioritizes adaptability and generalization.
You're right, it's like we're not just building all-knowing AI systems, but AI systems that can learn and adapt like we do. Which brings us to another interesting aspect of the paper, the comparison between child tuning and model pruning. Can you unpack that a bit?
Of course, there's a vital distinction between the two. Both involve selecting a subnetwork within the larger model, but their goals are different. Model pruning is all about efficiency. It's like decluttering a messy room. It identifies the parts of the model deemed unimportant and removes them completely, sacrificing some knowledge for the sake of speed and a smaller memory footprint.
So it's about streamlining the model, making it leaner and faster. How is child tuning different?
Child tuning, on the other hand, is like focusing a child's attention on the most important subjects, while still allowing access to other areas of knowledge. It keeps all the parameters intact, even those that are not part of the child network. The non-child parameters are frozen during training, but they still contribute to the model's overall knowledge base.
I see. So it's like the difference between deleting files from your computer versus moving them to an archive folder.
Exactly. They're still there if you need them, but they're not cluttering up your active workspace. And the paper backs this up with some really interesting experiments. They did what are called ablation studies, where they tested what happens if the child network is selected randomly. Instead of using Fisher information, the results showed that random selection did help a bit. But targeted selection based on Fisher information was the key to child tuning success.
So the curriculum matters. Just like a well-designed curriculum can make a huge difference in a child's education.
Absolutely. Choosing the right parameters for that child network is crucial.
And they even tested selecting parameters with the lowest Fisher information. What happened then?
It led to terrible performance.
That's really telling. It underscores the importance of selecting the right parameters, the ones that are truly relevant to the task at hand.
You got it. Task awareness is essential.
Did they mention anything else about comparing these different approaches?
Yes, actually. They included a visualization showing the overlap between child networks selected for different tasks. And they found that similar tasks tended to share more parameters. For instance, tasks related to sentiment analysis might share a large portion of their child networks, while tasks involving question answering might have a different set of overlapping parameters.
That makes sense.
Yeah.
It seems like child tuning is tapping into something fundamental about how these language models represent knowledge. Different tasks rely on different underlying capabilities, and child tuning can identify those shared and distinct parameters.
Exactly. It's like different subjects in school. They might share underlying skills like critical thinking, but also require specialized knowledge. Child tuning seems to be capturing that complex interplay between general and task-specific abilities.
This has been incredibly insightful, and I feel like we've only scratched the surface. But for now, we'll have to pause here. Be sure to join us for part 2 of this deep dive, where we'll explore the potential implications of child tuning and delve into some of the questions that have me so intrigued. Welcome back to the deep dive. I'm still trying to wrap my head around all the insights from part 1, the results on the GLUE benchmark, the generalization experiments. Child tuning is clearly a powerful technique, and that child analogy, it really helps grasp this selective learning approach.
It is a powerful metaphor. It highlights a change in our thinking about these massive models. We're moving away from that idea of brute force training, where we just throw a ton of data at the model and hope for the best. Child tuning is more about finesse, carefully guiding the learning process, focusing on the most relevant aspects of the model.
Exactly. It's like we're not just training these models, we're educating them, providing them with the tools to learn and adapt, much like how we nurture a child's development. Okay, so we've established that child tuning works wonders with language models, but the paper leaves us with this intriguing question. Could this concept extend beyond language? What are your thoughts on that?
That's where things get really exciting. If we step back and look at the core principle of child tuning, this idea of selectively updating certain parameters to prevent overfitting, it could potentially be applied to any field where we're dealing with large models and limited data.
So we're not just talking about language anymore. We could be talking about image recognition, medical diagnosis, financial forecasting. The possibilities seem endless.
Exactly. Imagine working on a project with a deep learning model for medical image analysis. You want to train it to detect a rare disease, but you only have a small data set of images. With traditional fine-tuning, you run a high risk of overfitting. The model might learn to recognize those specific images perfectly, but fail to generalize to new cases.
And that's a critical problem in medicine. We need models that can accurately diagnose new patients, not just memorize the training data. How could child tuning help in that situation?
Instead of retraining the entire model on that small data set, we could use child tuning to zero in on specific features that are most relevant for identifying that rare disease. You could use Fisher information, or a similar technique to pinpoint the parameters that are most sensitive to variations in the disease diagnosis.
So it's kind of like training a medical student to specialize in a specific area.
Yeah.
You wouldn't expect them to be an expert on every medical condition, but you'd want them to have a deep understanding of their chosen field.
That's a great analogy. And by concentrating the training process on those critical parameters, you could potentially boost the model's accuracy significantly, while also reducing the risk of overfitting.
It makes perfect sense. And thinking beyond medical diagnosis,
Huh?
could child tuning also be helpful in areas where efficiency is crucial? We've talked before about the growing concern of the energy costs involved in training these massive models. Could child tuning offer a solution there?
Absolutely. By updating only a subset of parameters, child tuning can drastically cut down on the computational resources and time needed for training. This could democratize access to these powerful models for researchers and developers who don't have the resources for massive computing infrastructure. And yes, it could play a crucial role in making AI more sustainable and energy efficient.
That's a major advantage, especially as these models become increasingly larger and more complex. Making these technologies more accessible could accelerate advancements in countless fields. But apart from the practical benefits of efficiency and accuracy, there's another aspect of child tuning that I find fascinating, the emphasis on generalization. It's not just about making the model good at one specific task, it's about empowering it to adapt to new, unseen data, and even entirely new tasks.
I agree. This focus on generalization truly sets child tuning apart. Traditional fine-tuning often leads to models that are highly specialized but brittle. They excel at the specific task they were trained for, but struggle when faced with something new. Child tuning seems to be pushing us towards a more robust and flexible form of AI.
It's like the difference between someone who has memorized a set of instructions versus someone who truly understands the underlying principles. The person who understands the principles can apply their knowledge to new situations, even if they've never encountered those situations before.
Precisely. And that's what we're aiming for in AI, creating systems that can learn and reason like humans, systems that can generalize from experience, and solve problems they've never encountered before. Child tuning represents a significant step towards achieving that goal.
So it's not just about making AI smarter. It's about making it more adaptable, more resilient, more like us. It's a real paradigm shift in how we think about AI development. As we wrap up this part of our deep dive, What are the key takeaways you'd want our listeners to remember?
I think it's crucial to understand that child tuning is a potent technique for fine-tuning large language models, especially when data is limited. It consistently outperforms standard fine-tuning methods, leading to substantial improvements in accuracy and generalization.
And equally important, the concept behind child tuning. The idea of selectively updating model parameters has the potential to transform how we train and adapt models across a wide range of fields. Not just language, we've talked about medical diagnosis, but the applications extend to practically any area where data is scarce or computational resources are limited.
Exactly. But beyond the technical aspects, I believe the most important takeaway is this. This research is moving us closer to creating AI systems that can learn and adapt like humans do. It's a reminder that intelligence isn't solely about computational power. It's about the ability to generalize, to learn from experience, and to apply knowledge in new and inventive ways.
Beautifully put. And that brings us to the end of part 2, but we're not finished yet. Join us for part 3, where we'll tackle some remaining questions
Yeah.
and explore the implications of this research in even greater depth. Welcome back to the deep dive for our final exploration of child tuning. As we discuss this research, I can't help but think we're on the verge of something truly groundbreaking in AI. It's not often that you come across an idea this impactful.
Yeah, I agree. There's an elegance to child tuning. It's intellectually satisfying and incredibly promising. It challenges our assumptions about how we build and train AI models, pointing us toward a more efficient and nuanced future.
Like we've been so focused on creating these massive, all-knowing AI systems that we missed the power of selectivity. Maybe true intelligence isn't knowing everything. Maybe it's about knowing what's important and being able to adapt. Kind of like our own brains, we don't use every neuron for every task.
That's a great point. Our brains are so efficient at filtering information and focusing on what's relevant. Child tuning seems to be using that same principle, selective learning and adaptation.
So maybe the next level of AI isn't about bigger models, but about models that can learn and adapt more like we do. Models that can focus, learn from limited data, and generalize their knowledge.
That's a really interesting idea, and it highlights the importance of research like this. Child tuning isn't just about benchmarks. It's about changing how we think about AI and its potential.
All right, as we wrap up this deep dive, I wanted to get your perspective on some of the questions that have been on my mind. Maybe you can share some insights with our listener as well. The paper was about language models, but we've talked about the potential for applying child tuning to other areas. What challenges do you anticipate in adapting it to things like image recognition or robotics?
That's a good question. One potential challenge is the concept of Fisher information, which is used to identify those important parameters in child tuning D. It might need to be adapted for different data types and models. Images and robots have very different structures than text.
So we might need new ways to measure that task relevance of parameters. It's like using the same teaching methods for artists, musicians, and athletes. You have to tailor your approach to each group's specific skills.
Exactly. That's where the creativity of researchers is so important. We have to find ways to translate the principles of child tuning to different areas, while also considering their unique characteristics.
And what about the computational aspect? We talked about how child tuning could make things more efficient, but could it also introduce new complexities, especially with different data types?
It's definitely possible. The implementation of gradient masking, which is a core part of child tuning, might need to be optimized for different architectures and hardware. There might be trade-offs between efficiency gains and the overhead of managing those updates.
It's a balancing act then. We have to weigh the costs and benefits of using child tuning in different situations. Here's another question I've been thinking about. How do we figure out the best size for the child network? Is there a set formula, or does it depend on the task and the model?
That's a question researchers are still working on. The paper offers some starting points, but finding that optimal size will likely involve a combination of testing and analysis. Things like the model size, the amount of data, and the complexity of the task will all matter.
So it's about finding that sweet spot, balancing performance, generalization, and efficiency for each application. And that leads to another thought. What about combining child tuning with other new AI techniques? We're seeing a lot of cool developments in areas like meta-learning and few-shot learning. Could there be synergies there?
Definitely. That's a really exciting area for research. Imagine combining child tuning with meta-learning. We could have systems that not only learn from limited data, but also learn how to learn more effectively. They could adapt quickly to new tasks and domains.
It's like teaching the AI to study better. That could be a real game changer.
It really could be. And it speaks to the impact of this kind of research. Child tuning is more than just a new technique. It's inspiring new ideas and approaches in AI.
It's a great point to end on. We've gone deep, explored the technical details, considered the bigger picture, and hopefully sparked some new ideas for you, our listeners. So keep learning, keep exploring, and keep pushing the boundaries of what's possible with AI. This has been The Deep Dive.